Yeah, thanks a lot, Günther. Yeah, actually, I would have loved to travel to Vienna, but unfortunately, my right knee is torturing me, and I still have to take painkillers. So I wouldn't pass any doping test at the moment. And I'm not that fast anyway, and now I'm even slower than usual, and I'm pretty sure that I will have too many slides anyway. That's our Sonderforschungsbereich, Collaborative Research Center. This is, of course, before Corona. You see, it's an old photograph. The geography of the Ruhr area is the following. As you have the river Ruhr here, the Rhine. Then here's Ruhr University Bochum. Then there is Essen, Mülheim, and Duisburg. So you see the four major sites. They are all lined along the river Ruhr, also in the heart of the Ruhr area. Two universities collaborating, Universität Duisburg-Essen, campus here, campus there. And we are very grateful for the Max Planck Society for supporting us. That's the Max Planck Institute for Chemical Energy Conversion in Mülheim. And of course, the Fritz Haber Institute in Berlin. And you see here Beatrice Roldan and all the others who participate. Actually, when we started our Collaborative Research Center, we were quite surprised that quite a few others started as well, and that has grown in the meantime, and they have collected here the logos of the other ones, the newer ones, and you see also there's quite some activity in catalysis going on in Germany right at the moment. The topics are different. You see here that's more on photocatalysis, ionic liquids, porous systems, homogeneous catalysts anchored in it. So it's really nice to have such a vivid scene, and that is organized within a loose network then called Catalysis, also where we organize joint meetings, joint talks. Okay, so it's what I'm going to talk about is mainly about cobalt oxide, and I will start in the gas phase and then gradually move into the liquid phase. And I think the liquid phase part that will have to be shortened a bit, because I think you will be mainly interested in the gas phase part. Yeah, it's about liquid oxidation catalysis, and we do it either as thermal catalysis, this is what I'm going to talk about, or we do it in electrocatalysis. And you know well that cobalt oxide is a famous catalyst for the oxygen evolution reaction, but that would be then Wolfgang Schumann's or Christina Schulich's talk. And we apply our catalysts in both fields, thermal and electrocatalysis, and we tried to establish links. We have more or less finished the first 4 years. Actually, the evaluation was last week on Tuesday. Also quite an event, and I think we did rather well, and now we are hoping for 4 more years, and that will be decided end of May. Also, but having survived this evaluation, we are quite confident now. The approach is that we prepare numerous samples. This is then called comparative study, just to establish a database, and then we characterize the catalysts. We look for links between especially the real structure meaning the defects that are actually there, and try to correlate that with activity. And the other pillar, that's the modeling of reactivity. We try to apply as many techniques as possible to characterize our samples, and the holy grail is then, of course, to perform operando studies. And in the liquid phase, that is actually quite a task. You will see in the following where the problems are. And I should mention that actually we had planned even to include photocatalysis. Then cobalt oxide would have acted as a co-catalyst on a photoabsorber. catalyzing oxidation reactions, but we decided to focus on these two fields in the next 4 years, because also the other CRCs have quite some photocatalysis in them. The structure of our CRC is not that surprising or overwhelming. We have to synthesize the catalyst, we have to characterize them as deeply as possible, and then we have to test them. So we have these 3 classical areas: reactivity, catalytic properties, that's so to say another way to characterize the cobalt oxides. And method development is highly important also in theory. In the beginning, we were not really that aware of that. We have, of course, very pronounced magnetic properties, and that complicates the application of theory quite a bit. Yeah, and this would be then this comparative study. We take the same catalyst, we apply different oxidants. Yes, it's not only oxygen that is the oxidant, but also peroxides that can be used in the liquid phase. We have different molecules that we want to oxidize selectively, of course. Just getting CO2, that would be waste. And in this way, we establish landscapes where we want to learn more about our catalysts. Liquid phase, this is a nice photo. That is usually occurring, yeah, how shall I say, behind stainless steel walls, because when you work with oxygen, you have to pressurize simply because of the limited solubility. And then you have an autoclave, also pressurized vessel, commercial one, where you have very little insight what's going on. And this glass reactor, that is just to have something nice on the photo. Yeah, so let me start now with gas phase oxidation. I call myself an industrial chemist, so that is in between, yeah, reaction engineering, that would belong then to engineering. And in Germany, we have this tradition of technische Chemie, that is kind of the link to engineering. What it means is that actually the reactor is the most important tool that we use in our research. When you are looking for the reactor, it's actually here. It's a small U-tube reactor. We fill in 100 or 200 milligrams of sample. We pass gas through it. We try to establish plug flow conditions. And then we have a mass spectrometer that's actually behind the setup that is calibrated. And what I will show you in the following, that although it's a rather simple setup, you can perform really a multitude of different experiments, steady state ones, transient ones, temperature programmed experiments. You can dose liquids and so on. Key feature is this calibrated mass spectrometer. Yeah, we received the samples from our collaboration partners, powders. The powders are filled into this U-tube. Then they are first conditioned. That is an oxidative pretreatment. This is to make sure that we get rid of any hydrocarbon residues that may originate from the synthesis. Then the cobalt is in the fully oxidized state. That would be cobalt 3 or 4 under our conditions. Then we switch to reaction. We feed 2-propanol and oxygen 1-to-1. Actually, it's a surplus of oxygen because it's O2. And then we run a temperature ramp up and down. It's rather slow. You see time scale here is hours. And then we repeat the same experiment. It's a quasi-steady state experiment. That means we monitor conversion, selectivity when temperature goes up and down. And by repeating it, we check for reversibility. Heating ramp is then just 0.5 Kelvin per minute. That is like running quasi-steady state, many temperatures covered then in such a simple ramp experiment. Now, major question, why do we want to oxidize 2-propanol? From an industrial perspective, it's not attractive. That is something I have to admit. But from a fundamental point of view, it's an interesting molecule because it's well established in heterogeneous catalysis that with 2-propanol, you can both probe redox properties and acid-base properties. Redox properties, either the catalyst catalyzes just dehydrogenation to acetone and hydrogen, or in the presence of oxygen, it can catalyze oxidative dehydrogenation. And when you do so, then the coupled product is water. Acid-base properties means that 2-propanol is converted to propene. That's something I'm not going to talk about today. That is mainly related to iron ions being present in the surface, or unwanted, it's just total oxidation. So that means by using such a simple molecule like 2-propanol, we can probe 4 pathways at the same time. And then in this way, we learn a lot about the catalytic properties of the exposed surfaces. The samples we get from our partners are a bit special. These samples originate from Stefan Schulz's group in Essen. He's using a molecular precursor, cobalt acetyl acetonate, and that is decomposed thermally in a high boiling solvent. In this way, he generates cobalt monoxide nanoparticles, and when we calcine them, we have phase pure cobalt 3 or 4. And that is a TEM image. You see many of these more or less spherical particles aggregated, and we can just take them as they are and fill them into the U-tube reactor. We need powder X-ray diffraction to check for phase purity, and TEM tells us that the mean particle size is 9 nanometer. That is rather small for an oxide, and the consequence is that the specific surface area is quite high. 43 square meter per gram, that's quite a lot. So we have many exposed cobalt oxide surfaces. It's a reactive system, and that we can probe nicely using 2-propanol. In industry, you would never use such a fine powder as catalyst that only works in small reactors. In industry, you would have to use pellets, but that is then a different story because then you have to enter mass transport limitations. In our case, it's kind of a perfect catalyst for a small reactor, low pressure drop. It's a non-porous catalyst, that I should say as well. It's just exposed outer surfaces of spherical nanoparticles. Okay, now we start the first heating experiment. We heat up in 2-propanol and oxygen. We monitor conversion, and you see we convert 2-propanol, then conversion decreases, and then we go up to full conversion. Oxygen is consumed as well, so oxidative dehydrogenation seems to go on. And when you look at your mass spectra, then you see immediately and are happy that it's exclusively acetone that is formed. Acetone plus water. So we have a low temperature channel, then we are up at the highest temperature, then we cool down again. And when we cool down again, then you see immediately, we have lost this low temperature channel. The high temperature channel is still there. And when we heat up again, then we are always here. So that means this low temperature channel is only present once, directly after heating in oxygen. Later, I will show you in really very great detail that this is simple coking, so deactivation by coking, and that you can easily check just by heating in oxygen again, and then you're back to the nice low temperature channel. So low temperature activity, oxidative dehydrogenation, 100% selectivity to acetone. It's then inhibited during cooling and subsequent oxidation. And this high temperatures channel, that is rather stable. We can go up and down in temperature as often as we want. And here we are then a bit less selective. You see here, so there's also CO2 included at the high temperatures. We do form some CO2. Yeah, whenever you detect its oxidative dehydrogenation, then you have to ask the question, is the oxygen of the catalyst involved? So is it gas phase oxygen that ends up in water, or is it oxygen originating from the catalyst, the cobalt-3 or 4, that is actually a bit reduced and produces water in that way? And this can easily now be probed by temperature-programmed experiments. We can adsorb 2-propanol and desorb it like in ultra-high vacuum. The only difference being it's now a much slower experiment, and we need a carrier gas, helium, to transport the desorbing molecules from the small fixed bed into the mass bag. And when we adsorb 2-propanol and start the heating ramp, then you see immediately, oh, fine, we get acetone and water, telling us it's the oxygen from the catalyst that is ending up in water. Here, there's no oxygen in the gas phase. It's a TPD experiment. And then when we go up to higher temperatures, then of course we get a lot of CO2 and water. So that means we have proven it's this oxidative dehydrogenation. You don't even need the gas phase oxygen for that. But of course, when the surface oxygen is consumed at higher temperatures, then you have a totally unselective system. You can make the experiment a bit more complicated. You adsorb 2-propanol, and then that is then called temperature-programmed surface reaction. Then you heat up in oxygen, and that allows you to monitor the consumption of oxygen from the gas phase. You start again with seeing acetone and water in the beginning, but then when we also detect oxygen uptake, then we see CO2 and water formation. Last experiment, what happens when we heat in 2-propanol only? Answer, nothing at lower temperature. Then we do observe formation of acetone and water, clear. Oxygen is taken out from the catalyst, but then we reduce cobalt oxide completely. So we convert the oxide into a metal carbon composite, and that metal carbon composite is then dehydrogenating 2-propanol. That means then we observe the release of hydrogen. So that means we have kind of irreversibly transformed the catalyst into a metal carbon composite. It's now pretty simple to summarize these observations. When you think about what is chemically needed to transform 2-propanol to acetone and water, then you inevitably arrive at such a simple cartoon. You need 2 cobalt-3+ ions to accept the 2 electrons and a nucleophilic oxygen anion. So nucleophilic meaning having a lot of negative charge, acting as a base. Here we have to break the OH bond and the CH bond, and then this oxygen ends up in water, and what is left is then an oxygen vacancy and 2 reduced cobalt ions. You know that mechanism from literature very well. That's the so-called Mars-van Krevelen mechanism that is also typical for high temperature gas phase catalysis. And what has happened now in addition, now you need oxygen from the gas phase to re-oxidize the active site so that we end up here again and can start the catalytic cycle again. And this is obviously what is present on our cobalt oxide catalyst after the calcination in oxygen, the 2 cobalt-3+ ions as electron acceptors and the anionic oxygen here that acts as proton acceptor. And there's also some nice literature from the old days from Guido Busca's group, who has already set up such a very plausible model. Yeah, the next question is now, so there seems to be this more or less labile oxygen that can be converted to water. Can we probe it directly by performing TPD experiments? And when you look at these TPD profiles here, then you see immediately, oh, the quality of the data is not that high. So here we have limitations. When you have a metal, you can perform TPD experiments with very great precision. With an oxide, it's much more complicated. What you can do is you vary the pretreatment temperature. You go up in pretreatment temperature. The more you do, the more you shift the maximum to higher temperature. You desorb more and more. But it's not really possible to clearly assign these peaks, and also the literature is quite confusing. All you do is you label them alpha, beta, gamma, but that is not really inside. Gamma, that's then for sure, that would be at even higher temperatures where you just by heating, you can convert cobalt 3 or 4 back to cobalt monoxide. That would be then a phase transition. As it's the lattice oxygen that is released at the highest temperatures, and the other species must be atomic oxygen or surface oxygen species like superoxide or O-. But what we still can do, we can integrate and correlate. Then, of course, we ask our colleagues from theory for help. In this case, that's Rosica Pencheva and her group. And you may have wondered, why did we decide to use Spinels and Perovskites as oxides? There are much more fancy ones. So one answer to that question is these are more or less simple cubic structures, and that's a major advantage for theory to work on them. That means these calculations can be performed with great care. These are DFT plus U terminations. We take the cubes, the B termination of the 001 facet. That would be the catalytic cycle now, completely. That is the starting point, the 2 cobalt 3 plus oxygen, 2 propanol adsorbing, forming the propoxide species, an OH group. That means we first break the OH bond, then we break the CH bond. We release acetone, we have the reduced active site, the oxygen vacancy, and that has to be refilled and reoxidized. And Rosica Pencheva made a more or less thermodynamic analysis. She was looking for the most favored pathway, and that would be the pathway down here, the red one, pathway D, where she says, okay, so according to this thermodynamic consideration, it's actually the Langmuir-Hinshelwood mechanism that is energetically more favorable than the Mars-van Krevelen mechanism, where you end up with an oxygen vacancy. And of course, oxidative dehydrogenation is thermodynamically downhill. When you do dehydrogenation, that means when you release hydrogen, then it's energetically uphill. Most important here is the message that presumably the active site, that's a cobalt 3 plus ion in an octahedral site at the surface, so it's coordinatively unsaturated. So it's a cobalt 3 plus 5-fold coordinated site. And as I said, we presumably need 2 of them. Now, question, why does this low temperature pathway disappear? That was very puzzling in the beginning. There are various options. One would be that we reduce the cobalt species too strongly. So we applied XPS, and these are Beatrice Roldan's Xane's data. We checked, of course, when you go up to high temperatures and under strongly reducing conditions, then you can perform even kind of a bulk reduction. When you look at the PS data before reaction, after reaction, you see it's not, there are not that many really pronounced changes. So there is some reduction, but that doesn't seem to be the main reason for this disappearance of the low temperature pathway. The way we tackle such problems is we solve the mass balance. So that's typical for engineering. That means we generate in oxygen, and then we monitor the amount of oxygen that is taken up, and at the same time we monitor the amount of CO2 and water formed due to oxidizing carbonaceous deposits. And it's actually the catalyst deactivates by coking. That is the result. Unsolved mass balance means we checked is everything that got adsorbed also desorbed, and we found there are quite a few carbon and hydrogen containing species that remain on the surface, and they are totally oxidized when we heat in oxygen to 300 degrees C. And that means we have, in this indirect way, identified coking. So that's the slang word for deposition of carbonaceous residues on the catalyst surface. Actually not that surprising. Then we were wondering, is there a difference when we regenerate in oxygen or when we make use N2O that actually comes from zeolite catalysis? N2O decomposes into N2 and O, so then you get atomic oxygen. So we wanted to check, is there a difference between molecular oxygen and atomic oxygen? And we found out, well, in principle, yes, but it's not that important. We can regenerate in both gases. We can regenerate in oxygen. We can regenerate in N2O. The reactivity is a bit different. O2 is more reactive than N2O. And you see immediately, okay, the low temperature channel reappears in N2O. We have to heat a bit higher to 573 K, 300 degrees C, whereas in oxygen it's sufficient to heat to 523 K. So both gases can regenerate. Yeah, and then we integrate the amount of CO2 formed, and then we see immediately, as soon as we start burning of coke as CO2, then we regenerate this low temperature pathway, and in oxygen that starts earlier. So we have already, after regeneration at lower temperatures, the low temperature channel back. One minor comment you see here, that actually this low temperature channel seems to consist of two channels, and I'm coming back to that later. Now the question was, can we learn a bit more about carbonaceous deposits? As it's a bit, yeah, not satisfying intellectually. Coking is well established, but you would like to know more about coking. And so we used diffuse reflectance infrared spectroscopy. The IR data are not that nice, but these are all black samples, and it's quite an effort where you have to dilute carefully with diamond powder to get spectra at all. So that was quite challenging to get this data. When you do adsorption, desorption with 2-propanol at room temperature, then you see the formation of the peroxide species. You have the 2 methyl groups that you can see nicely in the CH stretching band region. Here the CH, the CO band, that is then at low wave numbers. And this peroxide species stays. When you do it at higher temperatures, 503 Kelvin, then you get reaction in addition. And then, of course, you check for the CO stretching vibration that is there. That means we do see acetone. Then we get different, chemically different methyl groups that we can distinguish, so we can clearly identify the formation of acetone and other species. And the other species that was interesting, that is, of course, carbonate. That was the first guess, what else should be formed. But in addition, we saw carboxylate, also the symmetric stretch vibration of the OCO group at 1402 wave numbers. And this band here in addition, and that allowed us to identify acetate. So these bands here, not that large, but reproducibly formed. Now, chemically, when you start wondering acetate, what does that mean? Acetate means you break one CC bond in addition. It's a C2 species, and it's rather plausible that acetate is an intermediate on the way from propoxide species to CO2. These acetates can then easily be oxidized to CO2 and water, then you regenerate the initial state of the catalyst. We did some more spectroscopy with the help of the Fritz Haber Institute, even in situ, and we got there the impression that the carbonates just play a minor role, but it's really this acetate species that is key to understand coking. And now the straightforward experiment is now that you do a pre-adsorption experiment. When you pre-adsorb acetone, that is then this curve here, then you see very little changes. It's like the conventional low temperature, high temperature experiment. But when you pre-adsorb acetic acid, taking liquid acetic acid, purify it, attach it to your setup, bubble carrier gas through, and then heat up, and then you see immediately the low temperature channel is fully blocked. So that means pre-adsorbed acetic acid is indeed a very strong side blocking species poisoning our low temperature channel. That means we have learned a bit more about our catalyst. So acetate has a very strong influence blocking the active sites. This is now a cartoon summarizing the state of knowledge up to now. The key problem is the catalyst is a bit too reactive. It can break a carbon-carbon bond. In this way, we have then a C2 species. Here it's still C3. Acetates are strongly bound, and this is then knowledge taken from homogeneous catalysis. Acetates strongly interact with cobalt-3+. They even decarboxylate, then kind of just CH3 is left, and that is strongly reducing, killing our precious cobalt-3+ sites, which are the active sites for the dehydrogenation. So that was nice insight that we learned even a bit more about coking, that it's initiated by CC bond breaking, and that acetate is the main culprit, so to say, killing our active sites. Now the question, what can we do about it? I think you have also read Zbigniew Sojka's literature, as it's kind of overwhelming. He's publishing high quality papers every year, and he has established, nice name, a morphodrome of all the spinels. And the question is then, of course, when we have these more or less spherical nanoparticles, like shown here, that would be the cube octahedron, then we expose all kinds of facets. Is it possible by changing the relative amount of exposed facets to tune the reactivity of our nanoparticles? So that was the idea behind it. So can we have, for example, more of these 110 facets? And the answer is yes. There is a way to get more of them. And the way to go is, instead of having the 9 nanometer nanoparticles, you have to choose 19 nanometers. This is, of course, huge now. In metal catalysis, you would go the other way. Typically, you go to smaller and smaller particles. Here, it's really going to huge ones, which we got again from Stefan Schulz's group. Having larger nanoparticles, and of course, specific surface area is lower. But when we perform the oxygen TPD experiments or the 2-propanol TPD experiments, then we realize we can adsorb much more. That means the total surface area is lower, but what is exposed is more reactive. And the very nice result was, this is what you have seen before, the 9 nanometer particles, and now having the huge ones where we claim that now we have much more of these 110 facets. Here we see that the low temperature channel is stable. It's actually stable for days. You can go to this temperature and keep it running, full conversion to acetone. That means these huge particles don't deactivate anymore. Whether you can really identify facets based on TEM images, that would be a talk in itself. This is just a clever guess. We assume that we have more of them because we have larger particles, but we have not really solid proof for their presence, except that we have this very different stable reactivity. And now the question is, why is it more stable? Is it the interaction with 2-propanol that is different, or is it the interaction with oxygen that is different? And when we perform this heating in 2-propanol only, then we get the same profile that we have seen before. So it's not the interaction with 2-propanol that is different, but it's the interaction with oxygen. And now we can again solve the mass balance after running steady state catalysis. That was quite challenging for Tobias Falk, who did all these studies. The question is seemingly simple. We know how much oxygen we consume. We know how much CO2 and water is formed. Shouldn't we be able to calculate the amount of oxygen that is used for reoxidation of the catalyst? In principle, yes. And what this table tells us, yes, the larger particles actually need less oxygen for reoxidation. That means they remain in a more oxidized state. That means this reducing acetate poisoning is less severe. That means they are faster reoxidized. And then, of course, we asked Rosica Pencheva again for calculations now on the 110 surface. And this surface is very different. Now there is just 4-fold coordinated octahedral cobalt 3+, highly reactive, and a special oxygen species that is just 2-fold coordinated, as indicated here. And we think, supported by theory, that the presence of this oxygen species allows to have a stable catalyst because the larger particles are much faster reoxidized than the small ones. That would be here the pathway C, according to the Mars-van Krevelen mechanism, that is more favorable, according to theory, on 110 surfaces. Maybe you're still not convinced because I didn't show you any single crystal data, but this is as far as you can get having nanoparticles, spectroscopy, and theory. And here, the Pencheva group also calculated pathways, different transition states, as it's rather plausible that it is like that. These are not yet published results, and a different way to get Spinel nanoparticles by chemical vapor synthesis. That means the whole catalyst synthesis is performed in the gas phase at high temperatures. That means we get nanoparticles, but they don't agglomerate because everything is highly diluted in the gas phase. And these nanoparticles have then a very high structural quality. And this is now what you get just by inorganic solid state chemistry, site occupancies, when you go from the cobalt oxide to the iron oxide. So that is magnetite. inverse Spinel, and then you fill in more and more and more cobalt. Here is an important step because here you get for the first time then cobalt 2+ and tetrahedral sites, and then here you're in the regime of the normal Spinel. And you see again this sequence, cobalt 3 or 4 is actually the most active catalyst, very systematically. If you add iron, the low temperature channel goes down, also the high temperature channel goes down. And these samples allowed a very special way of structural analysis, a reverse Monte Carlo simulation of this structural data set simultaneously. And there it seems that we can establish a correlation between the low temperature, the middle temperature, and the high temperature channel, and we can correlate it with atom pair frequencies. Atom pair frequency means the likelihood that we have pairs of ions, cobalt on octahedral sites, octahedral and tetrahedral sites, and cobalt 3 or 4 always wins, is the best catalyst. So these are quite nice results, I think. Now comes a really big change. You may have realized that I like working in the gas phase because we have all these tools that can be applied nicely. But the title of our SFB is oxidation in the liquid phase. That means now we really have to use the autoclaves and work in the liquid phase. Here we used different samples that were made by nanocasting, that is Eco Budianto in Harun Tüsüz's group at Max-Planck-Institut für Kohlenforschung, the Schütz department. And this is done by hard templating. That means we get nanorods because the template had straight pores. These pores are filled, the template is removed, and we get again high surface area, not nano particles now, but nanorods. And this data set was highly valuable because here we incorporated, Eco Budianto incorporated just tiny amounts of iron. You see the cobalt to iron ratio is now 64 or 32, 16. So that means very little iron. And the question was, is there an influence of such a low amount of iron? And here you see the TEM images showing you the rods. Now the question how to run the reaction in the liquid phase. And again, Tobias Falk had to work quite hard to find conditions where we got some conversion. And 160 degrees C and 5 bar of oxygen pressure are actually quite harsh conditions. The reaction is still slow. That means it's running, as you see here, for 4 hours. And during 4 hours, conversion is still low, just up to 4%. But we do get systematic trends. Cobalt 3 or 4 is again the best catalyst, as in the gas phase. The straight line, the reason for that is because conversion is still very low. At high conversion, it would bend over. Yeah, and when we add now just a little bit of iron, conversion is less and less and less. We can plot that now in a different way, normalized reaction rate versus the cobalt to cobalt plus iron ratio. And then you see as soon as we add just a little bit of iron, the rate drops and even more, which is quite surprising. And one way to analyze this data is now we assumed that we need larger cobalt ensembles that form the active site. And when you do a mathematical analysis, these are these straight curves in here, then you can estimate that this cobalt ensemble is actually larger than 6 cobalt ions. And that would be one of the few ways how to explain that adding just a little bit of iron has such a strong catalytic influence, because then iron lowers the size of these cobalt ions. Now you ask, of course, the question, what is this small amount of iron doing? And I would say we still haven't found the final answer to that question. This is, of course, now related to long-range order. What we found by measuring Raman spectroscopy, that there is a certain disordering of cobalt-oxygen bonds. And by measuring X-ray emission spectroscopy, there was some indication that we changed the overall spin state of the cobalt ions. But this is still challenging for theory now really to come up with a plausible explanation. How can this small amount of iron, when you add it, lead to this huge drop in catalytic activity? And at least for perovskites, there are some indications that the active ensemble is indeed rather large, as much larger than the two cobalt ions I have shown you up to now for catalysis in the gas phase. Now, in between working under dry conditions in the gas phase and really working in water, what's in between is then using wet feed. That means we added water to 2-propanol and oxygen, checked what the effects are, and we saw that actually adding water is beneficial. Then we do some formal kinetic analysis to see analogies. And indeed, we got similar apparent activation energies in the aqueous phase and with water co-feeding during heating. So this is now the question, is the active site still the same when it's in liquid water? And of course, what you have immediately in mind is, can't be, it must be hydroxylated. And indeed, we saw the chemical reactivity of the catalyst is much lower. And there are ongoing molecular dynamics calculations that look at hydroxylation. OH minus is then much less basic than the oxygen anion, the O2 minus. So that means it's less likely that we form the propoxide, and it's then also the question, is it simultaneous bond breaking or first OH, then CH? That is still ongoing research. And we use this wet feed as an intermediate step between gas phase and liquid phase. Okay, then I will come to a rapid end. Then I will give you just a little bit of a flavor what then the real challenges are when we then really work in the liquid phase, and not just with 2-propanol as a probe molecule, but with molecules that are really of chemical interest, even in chemical industry. And the molecule we oxidize is cyclohexene, and we do it now in using acetonitrile as oxidant, as solvent. That means we dissolve cyclohexene in acetonitrile. We work in an autoclave. You see it here again. We pressurize with oxygen, and we don't go to too high temperatures for reasons I will show you in a minute. And now what we enter here now, that is now really chemical complexity in the liquid phase. What we do here is very closely related to what is going on in homogeneous catalysis, and we do learn a lot from homogeneous catalysis. We enter the field of peroxides as intermediates. So here, this allylic CH bond is broken. We form the hydroperoxide, and that decomposes then into the products we are interested in, the alcohol or the ketone. And in the end, when via the epoxide, we have the diol, and the diol can then be oxidized. We break then this bond here to adipic acid. That's a dicarboxylic acid used in industry for making polymers. So that means we have now huge reaction networks. And what you see in the next slides, we work with hydroperoxides and radical chain mechanisms. And this is now just one example, and then maybe I stop. Now we make use of the perovskites. In the perovskites, you can substitute the B position with iron, but then you see conversion, the gray bars. They don't increase actually they decrease, but you can also substitute lanthanum by strontium 3+, 2+. That means you have to compensate for the missing positive charge. And this can be done either by forming cobalt 2+ or by oxygen vacancies or by both. From a characterization point of view, that is pretty challenging. What we see with TEM is that when we increase the strontium content, we get more and more disorder, stacking faults. XPS tells us indeed we get more cobalt 2+, and counting oxygen vacancies, that would be a talk in itself. That is still an unsolved problem. And when we take now the best catalyst with 0.2 strontium in it, then we can perform formal kinetics, as in spite of the very complex reaction network, we can identify first order reaction kinetics. Then you have to check, are you limited by the oxygen pressure? You pressurize more and more, but you see that there's hardly any influence on selectivity. You vary temperature and can derive, just making simple Arrhenius plots, you can derive apparent activation energies for that catalyst. And the products you get, now you see it's mainly the ketone, also some of the diol, the hydroperoxide, that is this intermediate that has to be decomposed. And actually for the decomposition of this hydroperoxide, you need also now the cobalt 2+ ions that you get by substituting strontium into it. And to some extent, you get also the alcohol and some epoxide. As you see, that is now really chemical complexity, what you have to check always. So that is really a must. You have to check, can you reuse the catalyst? That means you filtrate, you use it again and again, and then you check, is it parallel or is it a bit decreasing? Is the structure of the catalyst changing to some extent, but still the catalyst is really rather stable. And the question is then, what is now the best oxidant? And we have now the choice, being in the liquid phase, it's not just oxygen, but we can also take hydrogen peroxide, H2O2, or we can take tert-butyl hydroperoxide as a more selective peroxide for oxidation. And then you see immediately, okay, oxygen, you can reach the highest conversion, most of the ketone, and so that seems to be the oxidant of choice. Yeah. Now I think I have to jump to the end with a few more comments. Now we made the same experiments also with substituted Spinel catalysts. Peroxide decomposition actually has old mechanisms. That is really Fritz Haber who is in here. And although you get nice formal kinetics, you realize, I think I have to jump here, that this is now a perovskite. You realize that this structural integrity is then in the end no longer given. I mean, when you look at here, it's iron substitute lanthanum cobaltite, complex system. It deactivates after every catalytic experiment, and ADX tells you what's actually the system is disintegrating, and that is of course a major drawback. You do your best during synthesis to achieve perfect mixing, phase purity, homogeneity, but during reaction the system may deactivate by segregation. And okay, then I'm jumping to the end. Last warning, you also have to check whether your solvent is really inert. And we made interesting experiences using another solvent. And actually this solvent is then part of the catalytic cycle because it's under reaction conditions converted to a hydroperoxide and takes part in these radical chain mechanisms. Okay, and then I would like to thank you very much for your attention. Yeah, actually I have forgotten to acknowledge all the co-workers. I should have acknowledged Daniel Waffel, Julia Büker, in addition, and also Bao Shang Peng, who is leading the selective oxidation group. Yeah, thank you again.